Hello everyone. In this lesson, we're going to learn about probability distributions and how to work with different probability distributions in Python. Now, many statistical tools and techniques used in data analysis are based on probability. Probability measures how likely it is for an event to occur on a scale from 0, which means the event never occurs, to 1, which means the event always occurs. When working with data, variables in the columns can be thought of as random variables, which are variables that vary due to chance. A probability distribution describes how a random variable is distributed, meaning it tells us which values a random variable is most likely to take on and which values are less likely. In statistics, there are a range of precisely defined probability distributions that have different shapes and that can be used to model different types of random events. So in this lesson, we're going to discuss some of the more common probability distributions and how to work with them in Python. To start with, we're going to look at the uniform distribution. The uniform distribution is a probability distribution where each value within a certain range is equally likely to occur, and values outside of the range never occur. If we create a density plot of the uniform distribution, it appears flat because no value is any more likely than another, so the density at any point within the distribution is the same. Now, many of the functions for working with probability distributions in Python are contained in the scipy.stats library. So to start off with, we're just going to load in some necessary packages for this lesson. So to illustrate what the uniform distribution looks like, we're going to start by generating 10,000 numbers from a uniform distribution and then plot them. So to generate some random data, we can use stats.uniform, that's saying use the uniform distribution, and .rvs is the function that generates random data. So we're saying generate random numbers from the uniform distribution, size equals 10,000 means we want 10,000 of them. And then loc and scale shows the range of where we want to generate from. So we're going to generate 100,000 numbers actually between 0 and 10. So we'll start by running that to generate the data. It might take a second because there are 100,000. And then we'll just use plot on it. So we'll turn it into a data frame and run .plot kind equals density to make a density plot. So the resulting density plot shows that with the uniform distribution, we essentially have a flat distribution here where any value within the range we specified from 0 to 10 is equally likely to occur. Now the scipy.stats package comes with some useful functions for working with probability distributions. We already looked at one of them. That's the .distribution.rvs function that generates random numbers from the specified distribution. So to use that, we already saw you say stats dot and then the name of the distribution you're working with. We were using the uniform, so we put .uniform there, but you can put other distribution names there too. And then .rvs, and that will generate random numbers from the specified distribution. The arguments to that will depend on the distribution you're working with. So for the uniform, we specified a starting and ending point. Other distributions will have different arguments, and we'll go into some of those later. But that's what you want to use to generate random numbers from a given distribution. There's also stats.distribution.cdf. The CDF, or cumulative distribution function, is used to find the probability that an observation drawn from the distribution falls below a specified value. So basically, the CDF gives you the area under the distribution's density curve up to a certain value on the x-axis. For example, with the uniform distribution we made above, there would be a 25% chance that we would see an observation between the range of 0 and 2.5. And a 75% chance it would fall between the range of 2.5 and 10 because of the way we constructed the distribution on the range from 0 to 10. And we could determine that using the .cdf function, so we'll just show an example of using that. We'll say stats.uniform.cdf for cumulative distribution function. We'll say we want to check the cumulative density up to the value of x equals 2.5, and then we'll use the same cutoff values at 0 and 10 that we used before. And when we run this, we see that there is a 25% chance that a value falls below 2.5 with this distribution. Now the stats.distribution.ppf function is essentially the inverse of the CDF function, it will return the x-axis cutoff value or quantile associated with a given probability. For instance, if we want to know the cutoff value, the x-axis value, for which we have a 40% chance of drawing an observation below that value, we could find that using PPF. So we'll give an example of doing that. Again, we'll do stats.uniform, this time .ppf function. The loc and scale will be the same. And here we're going to check a quantile of 0.4. So we're basically asking here, what x-axis value would we need to set to slice off 40% of the distribution to the left of it? So when we run this, we see that the x-axis value in this case is 4.0 because we made a uniform on the range of 0 to 10. Finally, the stats.distribution.pdf function gives you the actual probability density, which is the height of the distribution at any given x value. Now, since the uniform distribution is flat, all x values within the range of the distribution are going to have the same probability density. But x values outside of that range will have a probability density of 0 because they never occur. So to illustrate, we'll just make a little for loop here going from -1 up to 11 and print the density at each of those different x values. And we should see that -1 is not going to have any value because that's outside of the range of the distribution. 11 should also not have any density, but everything between that range from 0 to 10 should have a density of 0.1. So we'll run this and see that values outside of the range have no density at all. We can't get a value of -1 when we're on a uniform distribution that only goes from 0 to 10. Again, we can't see 11, but anything within the range, so some of these different values, all have the same density of 0.1. Now, before we go any further with this lesson learning different probability distributions, we're going to spend a second learning about generating random numbers in general and setting the random seed. So when you need to generate random numbers within a given range with even probability, you can just draw numbers from the uniform distribution using that stats.distribution.rvs function that we just saw. But Python also comes with a library called random that lets you perform various operations that involve randomization. So we'll look at a few of those functions. If we import the random module, we gain access to several functions that involve randomization. Firstly, we can use the random.randint function to generate a random integer from a specified range. So if we wanted to get a random number from 0 to 10, we could use randomint to do that. So there we generated 6. You can also use random.choice to select a random element from a sequence. So for instance, if we had a list of these 4 numbers and we wanted to select one of them randomly, we can use random.choice to do that. So if we run this, we should see an output of one of these 4 numbers. I don't know which one, but we will get one of them. And if you want to generate random real numbers on the range from 0 to 1, you can do that with random.random. If you want to get a random real numbered value outside of just the range of 0 to 1, you can instead use random.uniform to do that. It's basically drawing a number from the uniform distribution. So you can do random.uniform and then just specify your range. So in this case, instead of drawing from 0 to 1, we're going to draw a number from 0 to 10. Now notice that if we run this random.uniform function again, we're going to get different output for the number. We're generating random numbers here, so each time we run it, we see something different. Now, on the one hand, that's good because with a random number, we should be seeing different numbers every time because it's random. On the other hand, having results vary from one run to another is not necessarily a good thing if you want your results to be reproducible. You can ensure that your results are the same each time you run a function that involves randomness by doing what's known as setting the random seed. So the numbers generated by random number generators in Python and other programming languages are generally not truly random. They're what's known as pseudo-random. So they're actually created by a deterministic process under the hood that is based on some initial starting state or seed. And if you use the same initial state for the random number generator, you will generate the exact same numbers. So by initializing the random number generator's seed value to the same thing before running a function that involves randomness, you'll actually produce the same result, which is a good thing if you want your functions to be completely reproducible. So we'll give an example of how to do that here. So with the built-in Python random package, you can set the seed using random.seed, then just pass in an arbitrary numerical value to that function, and it will initialize the random number generator. Now, to show you that this actually does initialize the random number generator and you'll get the same results after setting the same seed, we're going to set the seed with 12. We'll generate some random numbers. Then we'll reset the seed to 12 again and generate numbers in the exact same way, and these will produce the same results here. So we'll run this and see that we produced the same random numbers, even though it wasn't random because they were based on an initial seed and then a deterministic process actually created them. So in general, these pseudo-random numbers generated by your computer are good enough for being random for most purposes, but just know that in reality, they aren't entirely random. Since computers are ultimately deterministic machines, they aren't capable of producing truly random numbers. So if you wanted to generate numbers that are actually truly random, you could do that by sampling some source of true randomness or entropy from the environment. So for instance, if you had a sensor hooked up to your computer that was sensing random atmospheric noise, and then you took measurements from that sensor over time, that could potentially be a source of true randomness. But for most purposes, the random number generators built into your computing environment or languages will be fine and may actually be desirable because you might want to be able to reproduce results exactly. Now, it should be noted that when you're using NumPy and the package is built on top of it, it actually has a different random number generator than the built-in random package in Python. So when you're using NumPy, SciPy, and other things built on top of NumPy for randomness, to set the random seed, you're actually going to want to use np.random.seed and then pass in a number to that function to set the seed when you're using randomness that's based on NumPy. Next, we're going to take a look at the normal distribution, also known as the Gaussian distribution. Now, the normal distribution is a continuous probability distribution, which means it can take on any values within its range, even fractional values, and it's characterized by a symmetric bell-shaped curve where the mean and median value are both at the exact center of the distribution. The bulk of the observations with the normal distribution will lie close to the mean. So as a general rule, about 68% of the data with a normal distribution lies within one standard deviation of the mean, while 95% of the data lies within two standard deviations, and 99.7% lies within three standard deviations. So if you hear people talking about things being 2 or 3 standard deviations away from the mean, they're talking about events that are fairly rare. The normal distribution is perhaps the most important distribution in all of statistics because it turns out that many real-world phenomena like IQ test scores, the range of human heights, and other things found in nature follow a roughly normal distribution. So it is often used to model random variables, and many common statistical tests and operations assume that distributions are normal or roughly normal. The SciPy nickname for the normal distribution is norm, so let's generate some normal data and investigate the shape of the distribution. So next we're going to generate a normal distribution plot to get a sense of what it looks like. You don't have to worry about all this plotting code, it's just going to generate a plot of a normal distribution for us to look at. But here we see what a normal distribution looks like in general. We have a symmetric kind of bell-shaped curve with about 68% of the data lying within one standard deviation of the mean. And there's about 16% of the data in each of the tails that are more than one standard deviation away from the mean. Now, in working with a normal distribution, it's common to have questions about the extremes or tails of the distribution and to want to know, for instance, how much of the data lies below a certain cutoff point or what the cutoff point is to cut off a certain amount of the data. So we can answer those sorts of questions with the normal distribution using the .ppf and .cdf functions we learned about earlier. We just have to use it for the normal distribution this time instead of the uniform. So we'll give a couple examples of doing that below. So for instance, if we wanted to take our normal distribution above and find the cutoff value or quantile value that cuts off 2.5% of the data to the left, we could do that using stats.norm.ppf, and we'll set our Q or quantile value to 2.5%. And we could do the same thing on the right hand of the distribution, so find the cutoff value for the 97.5th percentile by setting Q equal to 97.5. And when we run these, we can see that the cutoffs are approximately -2 and 2. Since this is a standard normal distribution, that means that approximately 95% of the data is within 2 standard deviations of the mean, because here this is almost -2 and this is almost 2. So that aligns pretty closely with the idea that about 95% of the data lies within 2 standard deviations of the mean for a normal distribution. And if we instead wanted to check how much of the data lies beyond a given cutoff value, so we're instead taking the cutoff value and saying what is the percentage of the data that lies beyond that, we can do that with .cdf. So here we'll do stats.norm for normal.cdf, and this time we'll ask it how much of the data is below -3, so that's about 3 standard deviations from below the mean. And we'll also say how much is above 3 standard deviations from the mean. And when we run that, we see that approximately 0.3% or so of the data is outside of 3 standard deviations of the mean. So that aligns with the general rule that 99.7% of the data for a normal distribution is within 3 standard deviations of the mean. So next we're going to move on and discuss the binomial distribution. The binomial distribution is a discrete probability distribution. Discrete meaning instead of a continuous function that can take on any value, a discrete probability distribution only takes on integer values. The binomial distribution models the outcomes of a given number of random trials of some experiment with a certain probability of success p. What the binomial distribution tells you is how likely it is to achieve a given number of successes in n trials of the experiment. For example, you could model flipping a fair coin 10 times using a binomial distribution, where you set the number of trials n equal to 10, because you're doing 10 flips, and the probability of success p equal to 0.5, since with a fair coin you have a 50-50 chance of a success. In this case, the distribution would be telling us how likely it is to get 0 heads, 1 head, 2 heads, and so on, up to 10 heads, if we were to repeatedly flip the coin 10 times. The SciPy shortcut name for the binomial distribution is binom, so we're just going to, again, generate some random binomial data here and then plot it so you can get a sense of what the distribution looks like. So we're going to make a new variable, fair coin flips. We're going to use the example that I just talked about. So we're going to model flipping a fair coin 10 times. So we're going to use stats.binom. We're going to generate random values from the binomial distribution. We want to have n equals 10 for 10 flips of the coin. We want a probability of 0.5, so it's a fair coin. And we're going to run 10,000 trials. This should give us a pretty good estimate as to what the binomial distribution will look like. So our plot should be pretty close to the actual underlying distribution, even though this is being generated from a random sampling here. So let's plot that. I created a table of the counts so we can see that, as you might expect, if you're flipping a fair coin 10 times, the chances you get 0 is pretty low. In 10,000 trials, we only got 0 10 times. So that's 0.1% of the time. Similarly, getting 10 heads in a row is pretty unlikely, so we only got that 14 times. So let's scroll down here and look at the distribution. You can see that with flipping a fair coin 10 times, we actually get what looks very similar to a normal distribution. Note, however, since this is a discrete probability distribution, we can only take on specific values of 0, 1, 2, 3, 4, etc. We couldn't get like 5.5. There's no such thing as half of a success in a coin flip. Since the binomial distribution is discrete, and histograms like this one model values in discrete bins like this, a histogram does a pretty good job of visually depicting what a binomial distribution looks like. As long as you use the proper number of bins, you can see up here we set bins equal to 11, which allowed us to capture the 11 different possible outcomes for this binomial distribution. Although this distribution is roughly symmetric and kind of reminds us of a normal distribution, that need not be the case depending on what the parameters we set for the distribution are. So in this case, we set a probability of success of 0.5. So the 50-50 chance means that our outcomes end up being symmetric. But if we set a different success probability, we would not get a balanced looking distribution like that. So let's generate a new plot using a different value for p. In this case, we're going to, again, generate 10 trials, but we're going to set p equal to 0.8. So that's an 80% chance of success this time. You could perhaps think of this as modeling something like shooting free throws. With a decent free throw shooter, you might be making around 80% of your free throws. So if we were to model this, it's showing us out of 10 shots, how often would you be making 1 shot, 2 shots, 3 shots, etc. At 80%, you might think you're going to be making 8 shots most of the time, but maybe sometimes you make 10. Maybe sometimes you're really unlucky and you only make 1 or 2. So let's run this and see what the new distribution looks like here. The table output actually shows us, even with 10,000 trials, there was no trial where you made less than 2 shots. So even on your most unlucky day, you're probably never going to be missing 10 shots in a row. And let's look at the distribution here. So we can see, as we might expect intuitively, making 8 shots is the most likely outcome as an 80% shooter, but making 9 or 10 shots or 6 shots also happens pretty frequently. Making less than 5 shots is very unlikely. With the .cdf function, we can check the probability of getting less than a certain threshold of successes. So if we wanted to check that probability of getting 5 shots or less, we could do that with .cdf. So stats.binom for binomial.cdf. We're going to check our k value here is going to be 5. So we want to check for 5 successes or less. And again, we're just going to set up 10 trials and a probability of 0.8. So when we run this, we see the chances of getting 5 shots or less if you're an 80% free throw shooter is about 3%. We could also check the probability of getting more than a certain value by using .cdf and just subtracting the value from 1. So if we wanted to, say, see the probability of getting 9 successes or more, we could check the probability of getting 8 successes or less. That's what this is doing. So k equals 8, the same parameters. And we just take that value and subtract it from 1. So that's essentially just saying get us the other side of the distribution. So instead of saying what's 8 and below, we're ending up with what's 9 and above. We can see we actually have about a 37.5% chance of hitting 9 or 10 free throws. Now for the continuous probability density functions, you use PDF to check the probability density or the height of the curve at a given x value. But for discrete probability distributions like the binomial distribution, you instead use .pmf, which stands for probability mass function, which checks the proportion of observations or mass of observations at a given number of successes k. So we can do that here for some different values. We just use stats.binom.pmf. So the probability of getting 5 successes when you're flipping a fair coin 10 times is about 25%. We saw that in the plot earlier. We could also run this with k equals 8 on our shooting example. So the probability of getting exactly 8 shots when you're an 80% shooter is right around 30%. Next, we're going to take a look at the geometric and exponential distributions. Now, the geometric and exponential distributions model the amount of time it takes for an event to occur. The geometric distribution is discrete and models the number of trials it takes to achieve a success in a repeated experiment with a given probability of success. And the exponential distribution is a continuous analog of the geometric distribution, which models the amount of time you have to wait before an event occurs given a certain occurrence rate. The SciPy nickname for the geometric distribution is geom. So let's use the geom functions and model the number of trials it takes to get a success or heads when flipping a fair coin. So to do that, we're going to use stats.geom for geometric.rvs. We're going to generate random geometric data. We're going to generate 10,000 data points. And the parameter of interest for a geometric distribution is the probability of a success. So in this case, we're going to use probability p equals 0.5 for flipping a fair coin. And this will model how many flips it takes before we get a heads. So we'll run this, generate a table, and plot the results as well. We can see that in our table here, half of the time about, it takes only one flip to get a heads. Well, that makes sense. Half of the time when you flip a coin, it's going to be a heads. And then 25% of the time about, it takes 2 flips, etc. Sometimes, if you're really lucky, you can get a lot of heads in a row. For instance, in one of our trials, out of 10,000 trials, we got 16 heads in a row. So if we scroll down and look at the distribution here, the geometric distribution tends to take on this kind of shape. A right-skewed looking histogram with a lot of the outcomes requiring only 1 or 2 successes, which happen fairly often, and with less likely outcomes, such as flipping 10 or more coins, way off in a long right tail. If we wanted to explore this geometric distribution further, we could use some of the functions we learned about before to check different cutoff values and areas under the curve here. So we could, for instance, use .cdf to check the probability of getting a success within the first 5 flips. So to do that, we could say stats.geom.cdf, k-value equals 5. Again, the parameter for probability, we're going to do a fair coin. So this is showing us the probability of getting a success in the first 5 flips. And if we take 1 minus this value, it's basically the inverse of that. So the probability of needing more than 5 flips to get a success. So only about 3.1% of the time does it take more than 5 flips to get a success. And similar to the binomial distribution, since this is a discrete distribution, we can use the .pmf function to check the probability of seeing a specific number of flips before a success. So if we wanted to check the probability of needing exactly 2 flips to see our first success, we could do that with stats.geom.pmf, k equals 2 for 2 successes, again, the same parameter for p, and we can see that 25% of the time it's going to take 2 flips to see a heads. Now we'll move on and look at the exponential distribution. The SciPy nickname for exponential distribution is expon. So let's scroll down and generate some random data from an exponential distribution to give you an idea of what they look like. So we'll run this and check the plot. So an exponential distribution has a similar shape to a geometric distribution. It's just a continuous version of it. So instead of having discrete bars, we have a curve here, and you can take on values between the integers. So we could have an outcome of, say, 0.5 or 0.6, where it takes less than 1 full time step in order for a success or arrival to occur. So basically what this is modeling is how long you would have to wait for someone to arrive with an arrival rate of 1. For instance, if we had a doctor's office and on average it took 1 hour for a patient to arrive, this is modeling how long you would actually have to wait for a patient to arrive. If the average arrival rate is 1, well, most of the time you're actually going to get an arrival that occurs in less than an hour, because you can see here that 63% of the data is actually less than 1. The reason that more than half of the data is less than 1 hour, even if the average arrival rate is 1, is that sometimes you have to wait a lot more than an hour to get an arrival. In some cases, you might wait 3 hours, 4 hours, even 5 hours in rare cases before someone arrives. So although those outcomes are very unlikely, so there's less overall area or mass on this side of the average, these occasional high values pull the average up. Now, to close out this lesson, we'll learn about one final probability distribution, the Poisson Distribution. The Poisson Distribution models the probability of seeing a certain number of successes within a given time interval, where the time it takes for the next success to occur is modeled by an exponential distribution. The Poisson Distribution can be used to model things such as traffic, or the number of arrivals in a hospital within a given amount of time. The SciPy nickname for the Poisson distribution is just Poisson, so let's generate and plot some random data from the Poisson distribution with an arrival rate of 1 per time unit. So it's similar to the exponential distribution we used above when we were talking about 1 arrival per hour. But instead of modeling how long it takes for that 1 arrival to occur, we're going to say how many arrivals are going to occur within a certain duration of time. So to do that, we're going to use stats.poisson.rvs, so we're generating random data from that distribution. We're going to generate 10,000. We're going to set mu equals 1. That means the average arrival time is going to be 1, just like we did with the exponential distribution above. And we're going to generate and plot that. So this plot is showing us that with an arrival rate of 1 person per hour, in an hour's time, we often actually see 0 arrivals. We also see 1 arrivals pretty regularly. We see 2 arrivals about half as much. But seeing more arrivals than that, like 3, 4, 5, or more arrivals in an hour, is pretty unlikely. So if we were, say, constructing the waiting room of a hospital, and we knew the average arrival rate was 1 per hour, we wouldn't want to make a waiting room that only had 2 seats, because we do see 3 or 4 arrivals sometimes in an hour, so we would need to allow for the eventuality that we might sometimes have hours that are more busy than normal. Now, while the exponential and geometric distributions were right-skewed, this Poisson distribution also looks right-skewed, but it doesn't need to be. It just is because of the way we set it up. The exponential and geometric are pretty much always going to look right-skewed. But if we used a Poisson distribution with a higher arrival rate, such as 10 people arriving per hour, well, if 10 people arrive per hour on average, we're not going to see 0 arrivals in an hour very often at all. So if we change that parameter to 10 arrivals per hour and replotted it, we would see a very different outcome here. So let's look at that. We're going to regenerate the data, but set mu equal to 10. So the average arrival time now is 10 per hour. And if we run that, we're going to see a distribution where there's going to be a lot more arrivals here. And if we look at a plot of it, now we can see that seeing 0 arrivals in an hour if 10 people arrive per hour on average is very unlikely. And sometimes with an arrival rate of 10, you even see 20 people in an hour. So in this case, you would need to plan for a fairly large waiting room for patients if you didn't want to have people standing. So to wrap up, Python's SciPy library contains a variety of functions that make it easy to work with a wide range of probability distributions, including many that we didn't discuss in this lesson. Probability distribution functions are useful for generating random data, modeling random events, and aiding with statistical tests and analyses. In the next few lessons, we're going to learn about how to create confidence intervals and carry out a variety of common statistical tests using Python. If you found this video useful, drop a like, hit subscribe, and I will see you again next time.